All right, we're going to continue our discussion of the production and cost structure of a typical firm. This coming from our chapter 7 in the OpenStax Intro Microeconomics textbook. And where we left off, we had discussed the typical shape and intuition behind the production function in the short run, the marginal product of labor, the inflection point that occurs when diminishing returns begins, when that extra worker adds less and less additional output due to fixed capital in the short run. And that led us to the structure of the total cost curves, total variable cost coming from labor, total fixed cost, what we can think of as our capital costs, and then the total cost, the sum of those two. So picking up the discussion from there, and this is basically where we left off, the mapping, if you will, between that production function that relates output per period of time to labor input, with the understanding, again, that the level of capital is fixed, and that inflection point where production goes from increasing at an increasing rate when we get those gains from specialization and there's plenty of capital to go around, then we hit that inflection point. The production function starts to flatten out. That additional worker gives less and less additional output. Marginal product of labor is falling. And that drives the shape of that variable cost and total cost function, with again the inflection point occurring when that slope goes from flattening to steepening on the cost side, and then our fixed cost, as the name implies, doesn't change as quantity changes in the short run. So in a sense, we're feeling a little bit like we we reached a plateau there where we were able to start to now answer the question that kind of set this discussion off, which was, wouldn't it be great if every firm had a mathematical function that would tell us what level of profit we would earn at a given level of output? And to do that, we had to find the cost structure. So how much would it cost us to produce any given level of output? We would subtract that off of our total revenue, and that would give us our level of profit. And again, we're going to circle back to this, but with the understanding that we have a pretty good idea of what's happening on the revenue side. Price times quantity, how does that change as production increases? It depends on the relationship between price and quantity demanded, which is dictated by our elasticity. And then now we have this total cost structure. So we can calculate both of those at any given point and come up with a resulting level of profit. And from that, we could be able to figure out, where is that profit level maximized? What would be the optimal level of output for a given firm? What we'll see, however, is that it's a lot easier, a lot more intuitive, and fits our model a lot better if we attack this question not at the total level, but at the per unit level, i.e., let's track the marginal benefit and the marginal cost of producing that one extra unit, and that will lead us to that optimal profit maximizing point. So we've got a few more items on our to-do list, which is going to be to reevaluate each of those levels of cost on a dollars per unit basis. And let's start with looking at our total costs on a per unit basis. So basically all we're doing is averaging across our units of output. How much are we spending in total divided by the total number of units we are producing? So that's going to give us our ATC, our average total cost. And it's going to be a really useful thing to know just on its own as a measure of production efficiency. Right? So as our average total costs come down for a given level of output, well, that means that we're able to produce that level of output with fewer resources. Because where do those costs come from? Our land, labor, and capital. So the more efficient a producer is, the lower those costs on average are going to be. And as far as the calculation, again, it comes right from the definition. Total cost averaged across our level of output. So it'll just be total cost TC divided by output Q. And obviously, numerically, we have these values at the ready to be able to calculate. But once again, we need this mapping, right? So what is the pattern of these average total cost as output goes up and down in the short run? Is there a place where we'll see an optimality, in this case, a minimum average total cost? And then how does that relate to the profit maximizing point? So in other words, we need that average total cost function. How do our average total cost values relate to the level of output? And then be able to diagram it, right, to get that visual. And we can do exactly what we did on the total cost structure, is just use the fact that the total can be decomposed into its components, labor costs and capital costs. So starting from that definition of total cost as the sum of total fixed and total variable, if we just divide that equation by Q, we get this relationship between the averages. So we know on the left-hand side, TC over Q, that's our average total cost. But we'll get the corresponding components here. So total fixed cost divided by Q, that's our average fixed cost, our capital cost per unit. TVC over Q will be our average variable cost. And if we add those two up, average fixed plus average variable, that'll give us our average total cost, our ATC. So what this allows us to do is to see how each of these components behave as output goes up and down, add those behaviors together, and we'll get the ultimate average total cost function. So just like we did at the total level, let's start with the easy part first, right, which is the fixed cost. So think about the equation here, our TFC over Q. Well, by definition, TFC doesn't change, but if we keep increasing quantity, we're going to get this shape that we see here. This continually declining capital cost per unit, because we're spending the same amount, but if we produce more, it costs us less per unit. So again, think of this as our capital cost, our rental cost per unit. And if it helps mathematically, it's going to look a lot like the first quadrant of that function y equals 1 over x, right? So the numerator is fixed, the denominator is increasing, and we'll get this asymptotic result, right? As quantity goes to infinity, hypothetically, our capital cost per unit goes to zero. Think about it in terms of, simple example, you you have a firm, they open up a brand new factory, it costs them $10 million per year to operate it. And on the first day that it's operational, they might produce one unit, one car comes out of the Ford Motor Company factory. Well, on that given day, they're spending $10 million. And if they only produced one unit, right, that unit would be $10 million in capital cost. So sorry, did that in the wrong order. As output goes to zero, going in this direction, our capital costs go to infinity, right? So we're producing a small number of units. It's going to cost us a lot per unit, flipping around how I started. As quantity goes to infinity, that average fixed costs go to zero. So now with that same $10 million factor, if we're producing 10 million units, it's only $1 per. Okay. So it's that spreading out of the overhead. The point is, it has a very predictable pattern, a very predictable shape, and it's entirely unrelated to that concept of diminishing returns and the inflection point, right? Because it's a fixed capital cost. So be able to explain why that average fixed cost curve looks the way it does, and if given some numbers, be able to do the calculations. Now, when we get back to the labor side of things, now is where we have to reconsider the impact of labor productivity, marginal product of labor, and that law of diminishing returns. As far as the definition, again, our average variable cost, our AVC, total variable cost over quantity, And note, right, we can't put a little line over total variable cost here. It's, of course, changing as output changes because when you produce more, you need more labor. You need to hire more labor. When you produce less, you can let labor go. And that relationship between how labor costs change with output, well, it depends on how much output you're getting per dollar spent on labor, which is the labor productivity. So, spoiler alert on the slide, right? The resulting function is going to have this U shape to it. So, initially declining and then coming back up. And you can probably guess why that is, right? Our labor cost per unit are initially going to start to fall when we have increasing returns before we hit that inflection point. So you hire an extra worker, they give you a lot of additional output for the amount that you're spending. So you give them a certain wage and you're getting a lot of additional output. So both costs and output are going up in that region, but output's going up faster. That's what's going to be happening here. Then, once we hit that inflection point, you keep going, you keep hiring that additional worker, you keep paying them the same wage, but you're getting less and less additional output. And now, put three up arrows in the numerator, our costs are rising faster than output because output is slowing down. So the cost per unit is going to start to rise, and we're going to see that upward sloping portion of that U-shaped curve. Now, the way we just described that, it's going to be really tempting to locate that inflection point right at the bottom of that curve because it's coming down. And then when we hit the inflection point, it starts to come back up. That's not quite where it's going to be. So let's hold off on that for a little bit. And we'll explain that at the end. But it does explain why the shape looks the way it does. Increasing returns, labor productivity increasing, labor cost per unit falling. Diminishing returns, labor productivity falling, cost per unit rising. Now we put those two things together, so we have that continually declining pattern in the average fixed cost. We have that U-shaped pattern in the average variable cost. Graphically, we add those two up and we'll get the resulting summation, the average total cost. So what we're seeing on this diagram is at any given point, we take the height of the average fixed cost, we add to that the height of the average variable cost, and we end up with the height of the average total cost. Probably easier to think about it this way, that the gap between average variable and average total is the average fixed at any given point. So we notice two things, right? With that average total cost curve, it's initially going to be sloping downward because both of its components are sloping downward. Average fixed cost always sloping down, and we're at the initial increasing returns component of the average variable cost. So they're both going to be coming down. So it's going to start at a really high level, but then start to come down. And only when the impact of diminishing returns that is pushing the average variable cost up, only when that kicks in are we going to see average total costs start to rise. So we're going to see another kind of vaguely U-shaped function sitting up above average variable cost. And with the gap between the two getting ever narrower, right, as that fixed cost starts to shrink, the gap between them starts to shrink. But once again, we get that same scenario. Why does this curve look the way it does? Because of the law of diminishing returns, right? Because of that labor productivity effect. That's what's driving the average total and the average variable. So my suggestion at this point is make sure that you can, have just a blank sheet of paper and sketch out just from memory and be able to explain a production function, a marginal product of labor curve, the total cost, total variable cost, total fixed cost, and now these three, average total, average variable, average fixed, and be able to say a word or two about why they look the way they do. be able to, pay close attention to the units of measurement on the axes, right? So this is dollars per unit versus output. Production function, it's output versus labor, marginal product, change in output versus labor, and then total dollars, and now dollars per unit. Okay, so one more important item here is the marginal cost. So this is kind of the ultimate calculation of dollars per unit from the producer's point of view. How much is it going to cost me to produce that one extra unit? So it's the change in your total cost due to a given change in output. New cost added per additional unit produced. Okay. Again, spoiler alert on the slide, we see that it's going to have this check-shaped function, and we can actually identify the inflection point as the bottom of that little check in this case. So the really short answer as to why this function looks the way it does, the cost per additional unit comes down, hits a minimum, and then jumps back up, is it's exactly the mirror image of that marginal product of labor function. We can also remember that it is the slope of the total cost function. So when that total cost is getting flatter and flatter, its slope is decreasing. When it's getting steeper and steeper, its slope is increasing. And what divides those two is where diminishing returns begins. So before we hit that inflection point, as total cost is getting flatter, labor is getting more productive. Good news for the firm, its cost per additional unit is going to be coming down. Once labor becomes less productive, the production function flattens out, the cost functions get steeper, so the additional unit adds more to total cost, so our marginal is rising. Okay. And right at the bottom of that point, right at the bottom of that function, I should say, is that inflection point. We can pinpoint, just like we can on marginal product, just like we can on those other graphs, where the diminishing returns effect kicks in. Right? So remember, it's the top of the marginal product graph, it's the bottom of the marginal cost. So think of those as mirror images. The labor productivity is driving the result that we see here. Now, one last item is that we want to put all of those graphs together, right? So the average total, average variable, average fixed, and the marginal are all measuring the same in the same units, dollars per unit produced. And the relationship amongst them is going to be really important in the ultimate solution, right? So we want to show how all those relate to each other. And we saw that on all of the averages, specifically how average variable and average total relate to each other. And we just want to see how our new friend, our marginal cost, fits into that scheme. Okay. So where do we put our marginal relative to the averages? And there's a very sensible relationship among these things. If we remember that the marginal is measuring the cost of that one extra unit that's being added to the average that we've already calculated, right? So a simple rule of thumb is that if the new unit that you're producing has a cost lower than the average, it's going to bring the average down. So when the marginal is below the average, you're going to see that average sloping downward. And then when we produce a new unit that costs more than average, well, once we add it into the calculation, it's going to bring the average up. So marginal above the average, average is going to be rising. I think that's pretty clear, but there's an obvious analogy for students, right? When we're tracking your grade point average, your GPA, you always have in the back of your mind, right? What is my current GPA and how is it going to be affected given my performance in this next class that I take, the marginal class, right? So if you come into this semester with a 3.0, so you've got a B average, and you get an A in this class, well, your marginal is above the average, so it's going to bring your average up after it's added into the calculation. If you have a 3.0 and your new class that you just finished, you end up getting a C, well, bad news, that's going to bring your average down. Same thing happens in the cost of production. The marginal is the new thing being added to that average calculation. So if we put all of that together, what that tells us is that the marginal cost curve, when we embed it in the rest of those averages, is going to be hitting the average total and the average variable right at their minimum points. So think about that average total cost. It's going to be declining as long as the marginal is below the average. And it's only going to start rising when the marginal is above the average. So the only way that can happen is if they intersect right at the bottom, right at the minimum of that average. And the same thing's going to be happening on the average variable cost as well. The new unit only has a marginal cost because of the labor. Right? So the average variable cost is going to keep declining as long as the marginal is below the average. So that finally answers, I know you were just waiting patiently, answers the question why we didn't label the minimum of the average variable cost curve as the inflection point. Well, because it's actually pushed past the inflection point a little bit, average variable keeps declining even when labor is getting less productive, as long as the marginal is below that average variable. So you get this little added area of declining average labor costs. And not until the marginal of the new unit is above the existing average is it going to start to slope upwards. So again, we're going to label the minimum, the bottom of that check, as the inflection point, the minimum of the marginal, not the minimum of the average variable. Related very much to labor productivity and diminishing returns, but the shape dictated by its relationship with the marginal. And no, we're kind of ignoring the average fixed since that has nothing to do with the marginal cost, right? And labor productivity. There's no structural relationship between those two. In other words, on a quiz or an exam, you can kind of draw those however the numbers dictate. Don't have to worry about finding any specific intersections. So this doesn't mean anything. But these intersections are going to be important. We have to draw them correctly, right through that minimum point, both of the U-shaped ATC and the U-shaped AVC. And then last thing, make sure that we have all of our cost curves kind of segregated appropriately by units of measurement, right? So these four can be shown all on the same diagram because they're dollars per unit. Total variable, total fixed, total cost have to have their own set of axes because the units of measurement are totally different. Okay, so now where we're going to go with this, we'll go through a numerical example. So we'll post up a video walking through that. And then we're going to revisit, circle back to that revenue question. What dictates the relationship between the level of output and revenue? Like we said, it's demand elasticity, which is dictated by the competitive environment that a firm is operating in. So this cost structure, we haven't made any distinction between, are we looking at a small firm in a competitive industry or a huge firm that's a monopoly? Because they all follow the same rules, diminishing returns and labor productivity and short run restrictions apply across the board. But on the revenue side, a small competitive firm is going to face very different restrictions than a large monopoly or oligopoly firm that has some market power. So that's where we will pick things up. And thank you for your attention.